In this section of the tutorial, we're going to take a look at the process of subsurface scattering as it occurs in the real world. I think most people have a basic understanding of what subsurface scattering actually is, which is the diffusion of light within a substance. But for most of us, that really is the extent of our knowledge. And that means that when we're confronted with the controls in our 3D software, we're a little bit baffled and we have to resort to a lot of guesswork. And so I think that having a better understanding of what actually happens in the real world will allow us to simulate those results much more convincingly in 3D. Now, of course, that comes with a caveat that no 3D software is a perfect simulation of the real world, but at least if we know exactly what it is we're trying to simulate, we're likely to achieve much better results. And so the very first thing that we need to understand is what happens when light interacts with matter. And actually, that question is relatively simple to answer because there's only a very limited number of things that can happen when light encounters a substance. And these are specular reflection, diffuse reflection, refraction, which you can also call transmission, and finally absorption, where the energy from the light is converted into heat. And that's it. Those are the only possibilities. And what lies at the heart of these interactions between light and matter is whether the photons in the light interact with electrons within the substance. So when the photons in the light encounter electrons that are near the surface of the substance, you get specular reflection. However, if the photons are able to penetrate slightly deeper into the substance, what's likely to happen is that they will be reflected multiple times by electrons that are bound to atoms within the substance, and the resulting reflection is a diffuse reflection. And this is why metals have no diffuse reflection at all, they only have specular reflection. And that's because metals, like all electrical conductors, have clouds of free-floating electrons that are not bound to any atoms. So when light encounters a metal, this cloud of free-floating electrons will immediately reflect the light away as specular reflection. But what about other types of materials? Materials that are not electrical conductors? Well, these have a completely different subatomic structure. In a dielectric material, you don't get this cloud of free-floating electrons. What you have instead is electrons that are bound to individual atoms. And that means that there is a lesser density of electrons within the material. And so the photons are able to penetrate deeper within the substance until they encounter an electron bound to an atom. And when that electron reflects the photon is then likely to encounter another electron bound to an atom somewhere else in the substance. The end result of this is that you get multiple reflections, and this means that the majority of photons that enter into the material are reflected multiple times and scattered in random directions, and this diffuses the light, which is why you don't get a sharp reflection from diffuse reflection. And so that, in a nutshell, explains the physical mechanisms behind the process of diffuse and specular reflection. But what about transmission? How does that work? Well, in the process of transmission, or refraction if you prefer to call it that, there is no interaction between the photons and the electrons within the substance. And that means that the light can pass straight through the substance without being reflected. And that's why we perceive materials such as glass or water to be transparent, because the electrons within those materials do not interact with the photons in the visible spectrum of light. However, what does happen when light moves from a substance such as air to a different substance such as water or glass is that the speed of the light will change very slightly. And this is what we perceive as refraction. We'll see some distortion that's caused by this change in speed. And there'll also be a small amount of specular reflection caused by the electrons on the surface of the material. Now, when it comes to the molecular structure of transparent materials, there's two different types. The first is the crystalline structure, and the second is the amorphous structure. And in the crystalline molecular structure, you get a rigid grid of molecules, such as you'd find in crystals such as quartz or diamonds, or even more everyday materials such as salt or sugar. Whereas the amorphous molecular structure is a more random and jumbled structure of molecules, and this is the kind of structure you would find in a liquid such as water, where all of the molecules are simply floating about freely, or also in a non-crystalline solid such as glass, which also has this amorphous structure. And these two molecular structures are also important factors when it comes to translucency, or what we call subsurface scattering. And in fact, most translucent materials fall into two distinct categories, the first being based on the crystalline molecular structure, and the second being based on the amorphous molecular structure. So let's look at the crystalline materials first. So while a solid crystal can be completely transparent, what often happens in nature is that you have many materials that are semi-crystalline. And what that means is that those materials are made up of tiny fragments of crystals all jumbled and crushed together. And so while all, or maybe even just part, of these crystals might be completely transparent, because they're all jumbled together and facing in different directions, what ends up happening is they disperse and diffuse the light that refracts through them. And I'm going to illustrate this concept with a material that everyone is familiar with, the sugar cube. If I was to ask you what color is a sugar cube, well, the obvious answer is that it's white. But why is a sugar cube white? Well, the answer is not as simple as you might think, because sugar cubes are not reflective objects like a white dinner plate, for example. A white dinner plate appears to be white for the simple reason that it reflects every wavelength in the visible spectrum of light more or less evenly. But that's not the reason why a sugar cube is white, because when you look at a sugar cube more closely, you'll notice that the individual grains of sugar are all transparent. And so, in fact, a sugar cube is a great example of a semi-crystalline material that everyone is familiar with. And so what happens when light encounters a sugar cube is that it will hit an individual grain of sugar and be refracted, and in that process it's bent very slightly and it's going to exit the other side of the grain of sugar facing in a slightly different direction and then immediately encounter another grain of sugar. And as this process is repeated thousands and thousands of times, as the light is refracted through multiple grains of sugar, what ends up happening is that the light ends up being diffused by these multiple thousands of refractions. So what happens when a photon encounters a sugar cube is that it's going to enter the sugar cube at one specific grain of sugar, and then it's going to be refracted hundreds or thousands of times through other grains of sugar until it leaves the sugar cube at a completely different point and facing in a completely different direction. And this process is how subsurface scattering happens in semi-crystalline materials. And there are a couple of other familiar materials that are made up of these relatively large crystals, such as the sugar crystals found in our sugar cube, and these would be salt and snow. There are also other materials that are made up of much smaller crystals that are much less obvious to the naked eye. And good examples of these would be things like marble or opaque quartz or ceramics and even some types of plastics. Now, one difference between the sugar cube example and a much denser material such as marble is that in the denser material, the light is not going to be able to travel quite as far as it would in a sugar cube or, for example, a snowball. And that's because all of the tiny crystals that are within the very dense material are much more closely packed. And what this means in practice is that the scattering distance in a denser material like marble is going to be smaller than it would be in a less dense material like a sugar cube. So now you should have a good understanding of how light is scattered within a semi-crystalline material. What about the second molecular structure, the amorphous one? Well, in this case, the resulting material is often an emulsion. But what's an emulsion? An emulsion is when one substance is suspended within another. And this is something that often happens within liquids. So two great examples would be orange juice or milk. And what is milk made up of? Well, it's mostly water, but within the water you have all these billions of molecules of fat. And the water itself is transparent, but the fat is opaque. So what happens when light encounters an emulsion? Well, obviously the photons can simply travel through the transparent watery parts, but once they encounter some of the molecules of fat that are suspended within the water, then of course they are reflected. But because that happens within the liquid and not necessarily near the surface, those photons that are reflected by individual molecules of fat are likely to encounter other molecules of fat suspended in the liquid after they've been reflected. So the main difference we have between these two molecular structures is that in the semi-crystalline molecular structure, the process that causes the diffusion is multiple recursive refractions, whereas in the amorphous molecular structure, this process is caused by multiple recursive reflections. And again, the density of the substance is going to play an important role in how far the light can travel before it exits the substance or is absorbed altogether. And so the denser the substance is, the shorter this distance will be. And so to give two familiar examples, you would get a much greater scattering distance in a glass of orange juice than you would in a hard, dense plastic. Now, in most people's minds, this concept of an emulsion is something that you associate with liquids, but it can also be found in objects that we consider to be solid. And this would apply to many organic materials such as plants or fruit or even human skin. But it can also apply to materials that have been manufactured. A plastic, for example, could have an oil base with a coloured dye suspended within it. But that doesn't mean that all plastics are amorphous. Plastics can be either semi-crystalline or amorphous. But let's return to organic materials for a second and let's think about why they might be translucent. So for example, why is something like a tomato translucent? Well, a tomato is mostly filled with water. And on the outside of the tomato, you have the skin, which is semi-transparent in that it's going to transmit some light into the tomato itself. And inside the tomato, you have millions of cells, and those cells have a membrane, which is also semi-transparent, so some light is going to get inside the cell itself, and within each cell you have mostly water, but with other particles suspended within it. So again, it's very similar to the emulsion that I talked about earlier. And this also applies to more opaque organic materials such as a plant stem or an apple. And of course, a very similar process also applies to human skin. The individual layers of skin are semi-transparent, so the light's able to penetrate into the flesh, and within the flesh you have millions upon millions of cells that have transparent membranes that are mostly filled with water and other particles suspended within that water. And so when it comes to organic materials, you can safely assume that the molecular structure is amorphous. The semi-crystalline structure is mostly found in materials such as rocks or in manufactured materials such as plastics. But essentially what is causing the subsurface scattering in both types of material is this combination of transparency and multiple recursive refractions or reflections. And the ratio of transparency to diffusion is going to have a profound impact on how translucent or opaque the material is going to appear. So for example, an orange segment is going to appear to be much more translucent than an apple segment simply because the apple is much denser. And that's simply because the orange is mostly water. And if you look at a material like marble, a thinner piece of marble is going to appear to be more translucent than a thicker piece simply because in the thinner piece there's just less opportunity for the light to get scattered. And so when it comes to designing your own materials, you should always bear in mind that there's a relationship between transparency and subsurface scattering. But that doesn't mean that all transparent materials are going to have subsurface scattering. Far from it. A material such as pure glass doesn't have any subsurface scattering at all. It is purely transparent. And that's because as the light travels through the glass, there is absolutely no interactions between the photons and the electrons in the glass, save for the 4% specular reflection that you get at the surface. So now that you have a basic understanding of the fundamentals of how light interacts with translucent substances, in the next section we'll take a look at how to think about designing your own materials.